Welcome back. Hopefully everybody found a nice lunch spot. All right, so we're moving on, and we have sort of put these talks into little sessions, and this one's titled Characterizing Tephra Deposits, Mineralogy, and Geochemistry. And so our first presenter is Nick Pierce, and he's going to be talking to us about future directions in trace element analyses using laser ablation ICP. Thank you.
Okay, well, good afternoon. If you've all had as light a lunch as I have, I'll forgive you for falling asleep in the next 25 minutes. Hang on, let's try that one. What I want to do is just talk a little bit about where ICP-MS is going and laser ICP-MS is going. And a few things now, as different people have started to use this technique, there are analytical issues that have started to sort of rear their head. And unlike the electron probe community, which has been running major element analyses on glass for the best part of 40 years, I suppose, laser ICP-MS is sort of where electron probe work was 20 years ago. And we need to get it sort of organized and sorted out. So there are some issues about how we do what we do. And also one of the things we lack seriously is reference materials for what we do. And do we need one? And you're not going to be surprised, I'll conclude yes. This is my partner in crime on the Yellowstone hotspot track a couple of years ago. And as a trace element analyst, I get material that comes from deposits like this, which is beautiful. And I get stuff that comes from things like this, in which somewhere there is one of Jill Plunkett's single grains of glass that she comes and asks me to analyse, okay? Somewhere in there is a crypto Tephra. And obviously this also gives us some slight problems in terms of what we do when we analyse this material. So this is the sort of stuff we're looking at. I mean, we've all seen glass shards. These are fairly typical for us. They're actually a little on the big side. This is the old crow Tephra. That's a 50 micron box up there, just to give you an idea. So these are quite chunky. These are some Huckleberry Ridge material. These are absolutely beautiful. You can park a car on these. They're so huge and very easy to analyse. And then the ice core guys I work with in Swansea come and bring me stuff like this, which is really rather difficult to deal with. And we need a technique, essentially, that will deal with that, or what's pretty typical. And it's not always easy. I wondered whether we'd see any sort of major and trace element data just to show why we need trace element data and what's what. So I sort of stuck these in at the last minute this morning, and Emma Gatti will talk about these tomorrow, right? And this is data from the from Toba, youngest Toba, middle Toba, oldest Toba. Major elements, you cannot separate these things at all. Very, very difficult to separate them on the majors. But once you start looking at trace element data, different colour scheme, I'm afraid. That's data from the oldest Toba tuff, 800,000 years, and these are 4 populations of glass in the youngest Toba that John talked about. As soon as you go to trace elements, you separate them perfectly, piece of cake. So that's why trace elements can be useful. You don't need them all the time, but sometimes they can be immensely helpful. So for trace element analysis of these things, we need a method which works for the tiniest grains up to gigantic grains, a few hundreds of microns across. And this gives us the opportunity to work on material that's from the proximal to the distal, several hundred, several thousand kilometres apart. But because we're working with things that are different sizes, are there problems in terms of how the analysis is performed? And most of the work we've done is on rhyolites, and that's what I'll concentrate on in terms of what I'm talking about. But there are some implications that transfer over to basalts, and essentially andesitic material is a nightmare to analyse, and I wouldn't really recommend anyone starts doing that ever. And if we then standardise methods, can it help us get data that we can rely on and can compare? And this is what the electron probe community has been doing for years with various inter-lab comparisons, the last one being the 2011 one that Steve Kuhn put together. Just for those of you who don't know what laser ICP-MS is all about, we've been working on single grain analysis by laser ablation ICP-MS since the late 90s. You fire a high-powered laser beam onto your piece of glass and vaporize the material, and then you compare an analyte element with an internal standard element, something like strontium over silicon, and then compare the ratio from your sample against a reference, a calibration standard, and the internal standard you use. We would usually use silicon, but calcium or silicon are used as internal standards. And this compensates for the amount of material that is vaporized from the sample by the laser. The focus varies, the grains some are a little bit more friable than others, and so on. And from this, we end up generating quantitative data for around 30 elements with accuracies and precisions, typically 5%, sometimes better, when we deal with 20 micron crater analyses. So that's about twice the diameter of a typical probe beam on these samples. And also in some of these things you can get isotope analyses and various other things, and there's a whole host of different things. One of the problems that is starting to become more apparent is that there is such a range of instruments around. There are several different generations of lasers that have wavelengths of in the ultraviolet, 193, 200, 213, 266. We've got green lasers and infrared lasers that operate with very short pulse lengths, and the pulse lengths are in the nanoseconds or the femtoseconds. Some cause problems of element fractionation at the sample surface, others don't, apparently. People use very different fluencies, that's energy densities at the sample surface. You can see that's sort of a factor of 30 in the amount of energy you put into your sample. That potentially is going to have an effect. The rates at which the laser fires, they're all pulsed lasers. For most of the work we do, 5 to 15 hertz is used. These femtosecond lasers fire at 200 hertz, which is a different thing. And then instruments, there's a whole host of different ICP-MS instruments, quadrupoles, sector field ones, reaction cell ones, multi-collector ones. Combine all those, just about every lab is using a different system effectively, which is potentially a problem. For internal standards, most people use silica or calcium, sometimes aluminium and sometimes iron. So again, possibilities of different calibration strategies. And the craters that people use, the smallest that virtually anybody can detect anything useful is around 10 microns, but we'll go up to about 50 microns in diameter for the ablation craters, although you see some people saying, oh yes, these glasses are beautifully homogeneous. And I saw one paper where somebody analysed things at 400 microns. Well, it's going to be homogeneous at 400 microns, isn't it, Christ? The car you parked on that glass shard would fall into the hole. It's that big, you know? Yeah, well, you know, okay. So this is the sort of stuff that we do on typical shards of glass. These are some Santorini glass shards. That's a 20 micron crater with our 193 nanometer laser. Beautifully round, circular ablation craters. A little bit of melt on the walls here. That's a 6 micron crater. And you get these melt films develop around the margins of the crater around here. And there are these things that possibly cause some problems. That little melt film around here may be partly responsible for the fractionation effects that take place in the ablation, or almost certainly to my mind they are. But you also get a bit of vaporization of the resin around it. This is epoxy that this is mounted in and so on. But generally they behave very nicely, these craters, and ablate things quite easily. Detection limits, well, for 20 micron craters, the detection limits for a whole host of useful elements are less than a part per million, typically, which is fantastic. 10 microns, you've got much less signal, your detection limits become somewhat worse, obviously, but still, the majority of the elements you're interested in are below a part per million at 10 microns. People who analyze at sort of 30 to 50 microns, yeah, fine for big pieces of glass, but for cryptotephra work, it's just not viable. These things are too big. Or some people occasionally will ablate the resin around it, but that brings its own problems. And because of various internal standard issues, at 20 micron craters or above, we are limited to using silicon as the internal standard in rhyolites. Calcium is too low to be quantifiable in rhyolites at 20 microns, if we're talking about these sort of high silica rhyolites with a percent of calcium in. And at 10 micron craters, nothing else can be used in those as an internal standard. Certainly on our system. It may be different on other systems, but certainly for us that's a problem. So we've got a detection limit issue about which internal standard we use. Are there any other issues about which internal standard we can use for the analysis, silicon or calcium? And yes, there are, if there are phenocrysts present in these rhyolitic glasses. And I just want to talk for a few minutes about what the issues of this presence of phenocrysts are. particularly with spot size, ablation spot size and choice of internal standard. And I was sitting down thinking about this, having read a paper where some numbers didn't match with our numbers on the same thing. And I won't mention any names, but a few of you will know the history to this. And I started thinking, well, what if you've got a random distribution of phenocrysts? In what is effectively a purified rhyolitic glass, we go through all the density and magnetic separations. We still find when we ablate individual glass shards, we hit things like feldspars, we get anomalous signals, we'll find the odd thing creeps through, and things with zircons in, or apatites and various other bits and pieces. So I started thinking about what this would do. That's 0.5% of phenocrysts by volume that's the surface of a glass shard. 20 micron crater would have roughly that cross-section, 50 micron crater that cross-section. And obviously, the bigger the crater, the more phenocrysts you ablate. By the time you get to 1% of phenocrysts, just about every 50 micron crater hits a phenocryst, whereas about 2/3 of the 20 micron craters miss them. And that's typically the rate of loss we have with our analyses. We'll find about 1 in 3 analyses maybe will hit a phenocryst at 20 microns when we do our analyses of that. For comparison, that's what the probe guys analysed, that tiny little volume there. So you can miss phenocrysts all over the place with a probe, you'll never see them. And even in backscattered imagery, if they're not exposed at the surface, you're not going to see one. And you're not talking big volumes of phenocrysts in these things. So I did this and expanded it into sort of 3 dimensions and modelled a cylinder and so on with some fancy Excel spreadsheets that took hours and did thousands and thousands of very, very tedious calculations with Excel. And this is what you end up with. 50 micron craters is this blue line here. That's the volume of phenocrysts in your sample. This is the number of analyses that have no phenocrysts in them. In 50 micron craters, just about every analysis will hit a phenocryst until you get below 0.5% of phenocrysts. So you're not analysing the glass, you're analysing a mixture of glass and phenocrysts at 50 microns. At 20 microns, by the time you get to around 1% or so, 60% of the analyses are clean. 10 microns, most of them are clean. It's fairly intuitive, really, when you think about it. But if you use big craters on these things, you are at risk of ablating phenocrysts. You can then calculate from that what the composition of the ablated mixture is. Take a typical plagioclase, mix it with a typical glass, work out what the vapour should be, and then see what happens if you use different internal standards by looking at the ratio of an analyte to an internal standard. So these solid lines here show the ratio of strontium against silicon as the internal standard, calcium against silicon as the internal standard, and ytterbium against silicon as the internal standard if you ablate into a plagioclase crystal. Now, if you ablate into a plagioclase, you would expect the vapor will have more calcium, it should have more strontium in it. And in this, when you use silicon as the internal standard, the strontium concentration goes up with the increasing volume of plagioclases. If you use calcium as the internal standard, bear in mind strontium is compatible in plagioclase, the strontium concentration goes down with more and more phenocrysts that you ablate. You don't see the ablation of plagioclase using calcium as the internal standard. The reported concentration you produce goes the wrong way because of it's to do with the ratio of calcium and strontium in the feldspar. So there's a danger using calcium as an internal standard in rhyolites. And this happens for any calcium-rich phenocrysts you care to think of in rhyolitic materials because of the low calcium in the rhyolites and the very high calcium in things like phenocryst, plagioclase, which is effectively ubiquitous in anything we look at, apatite, amphiboles, allanite, clinopyroxene. And some of these are very rich in trace elements. And you just don't see them. The concentrations do the wrong thing. And they only have to be there at fractions of a percent. So calcium is problematic as an internal standard in rhyolites, and I would urge any of you doing this not to use it. And I would stick with silicon if you can. It's a better choice and it's a safer choice. There is another problem as well of using calcium as an internal standard, and that's if you ablate the mounting resin that surrounds the grain that you've mounted it in. And mounting resins are a nasty mixture of all sorts of weird and wonderful polyatomic species, hydrocarbons, sorry, there's carbon, hydrogen, nitrogen, and so on. You ablate the resin, and the carbon in the resin reacts in the plasma, forms carbon dioxide. Carbon dioxide has a mass of 44. That's exactly the same mass as calcium that's used as the internal standard. So by ablating the resin, you increase the calcium counts, essentially, in the spectrum that you see. Nitrogen also reacts, and we get a big nitrogen blank on silicon, but you get nitrogen here, mix it with hydrogen, you get mass 29 at silicon. And this table shows some numbers for running just silicon and calcium in resin blanks that various people sent me. These are averages of a few different types of resin. The typical blank, we would get maybe 50,000 counts or so when we're not running a sample through the instrument, when we're just ablating, when we're just measuring the gas that runs through it. Ablate the resin with the conditions that you would normally use to ablate a grain, extra few thousand counts for each of these peaks because of these polyatomic species, nitrogen, hydrogen, or CO2, or whatever. And they give a 3, 4, 5% increase depending on what the conditions are. That increase of 2,000 counts on the silicon sample is insignificant when you get 1 million counts for silicon as your internal standard counts off your sample. 0.2%, trivial really, in terms of the added counts for silicon. For calcium, that 2,500 counts we got here relates to nearly 6% extra in the calcium signal that you get, which would reduce your numbers by 6%. Calcium internal standard goes up by 6%. Your concentration that you calculate effectively comes down by 6%. So there's a problem using that, and it's because of the low counts you get for calcium because of the low concentrations. So the internal standard choice is also problematic. If we hark back to that first picture of one of the holes I showed you, the ablation craters, actually that sort of volatilization of resin around the sample, because of just the local heating effect, will add to that signal. So even that, without deliberately ablating resin, is a problem. There was one study that, this is the rather contentious thing that vexed me a lot over Christmas this year, was some data that was run by 2 labs, mine and another one, on the same samples. And these guys used 50 micron craters and calcium as an internal standard to analyze their glass shards. We use silicon as an internal standard and 20 micron craters. Okay? And there, when you look at the ratio of the 2 sets of data, their data was about 40% lower than ours, consistently across the board. There's no way on any of these samples you could get a 50 micron analysis on clean glass. They were ablating resin and glass at the same time. And also, you might not be able to see it, but in several of these glasses, there are little hints of microcrysts and phenocrysts as well. And to my mind, that difference was the difference between the two. So you've got to bear that in mind. The problem with using silicon as an internal standard, which you don't get so badly when you use calcium as an internal standard, is fractionation. And fractionation is an effect that happens at the laser sample interface where elements don't vaporize off the sample quantitatively. So you get preferential retention of elements in the sample, you get preferential volatilization of elements from the sample. And this shows the effect of this with crater diameter across the bottom. We know the composition, this is from Santorini, from Minoan ash in Santorini, that's about 550 ppm is where the composition of that should be at 20, well, that's the bulk composition. And at 20 microns, we get around that. But at 10 microns, the concentration's lower down here, 6 microns lower still. And it's related to to crater size, and it's related to the volume of that melt film that forms on the surface of the crater. So the smaller the craters you go, the more problematic this becomes. Of course, we want to analyse cryptotephras. We want to analyse that 10 micron grain that comes out of a peat bog in Ireland. Well, I don't, but people do. And so we want to put holes in it that are this big, but there's this fractionation problem, and this needs to be overcome. And to overcome this, we can correct it based on reference materials. But, and this is again the next problem, the problem comes with the reference material that's available. The one reference material is around is a thing called AthoG. And AthoG is a remanufactured natural Icelandic obsidian. And you can analyse this and make these corrections for spot size. But it's not anything like the typical rhyolites that we work with. It's got 3.5% iron in it. It's jet black. We're typically colourless and about 1% iron. It's anhydrous, AthoG, compared to anything up to 6, 7, 8% water in some of our glasses. And you've got to ask the question, does it behave the same as a natural glass? And the answer is, I don't know. It may do, it may not. My gut feeling is it doesn't. But But there's nothing to test it against, so we can't tell whether it behaves right or wrong because we haven't got any of the reference materials. And the other problem with AthoG, it's heterogeneous as well at less than 50 micron spot sizes. So at a 10 micron spot size, what do? Once again, we're stuck. So John and I were talking over a coffee, Westgate and I were talking over a coffee in Aberystwyth last November, and we thought we'd really need some real glasses, real natural glasses. And John went back and looked at his set of data that he had, and we picked out a bunch of maybe about 10 separate Tephras that were homogeneous as far as the major elements were concerned, from Yellowstone, New Zealand, and so on. And we did a lot of laser work on them. We did some ion probe, or I did some ion probe work on them up at Edinburgh. And we found 4 of these that were homogeneous, that had RSDs on the abundant trace elements that were much better than the confidence limits on AthoG, within a few percent. So these look promising as reference materials. So nearly giving myself a nervous breakdown in the last fortnight, I put a NERC grant together just before coming out here, which was submitted literally about 2 weeks ago, and to try and get some money to go and collect a huge amount of these things and put them through a proper certification round to get some natural reference glasses certified to be used by the community as reference materials. And the aim of this, hopefully, will be to distribute these essentially at the cost of postage to anyone who wants them to use in their labs. And these will give us all sorts of other benefits. They'll tell us things about fractionation that we can check at different spot sizes, and they'll be useful for isotope systems and all sorts. So if any of you perchance get this grant proposal to referee, okay, you know what you got to do, all right? So hopefully, if we get this and sort this out, we'll do it. I suspect if it doesn't come off, John and I will try and figure out some way where we can do a sort of pared down version of this and produce something for at least one of these samples or so, and do it. There's a case of beer riding on it between me and Westgate as to whether we get this or not. Something that doesn't worry about fractionation, you're going to hear a lot more about this, but Steve asked me to sort of put these in, and I'm now at sort of 20 minutes, so I'll whistle through these next few things. Was lead isotope work, and a couple of years ago John came over again and we did some work on stuff from the Yellowstone hotspot track and looked at the lead isotopes on the ICP. We've got a single collector sector field instrument, and we looked at the different parts. This is the current Yellowstone caldera. This is the is that hazy, John? No, it's a bit old for that, isn't it? It might be some of the haze caldera ones, won't it? And then some of the older ones. The red one's Yellowstone. That's the current caldera, yeah. That's Bruno Yarbridge, that one, isn't it? Yeah, but all part of the hotspot track. But you can see the differences in the lead isotopes, and this is all obviously reflecting what's going on down at depth. But it's actually a useful fingerprint for these things in terms of where they are. And surprisingly, and we were super surprised at this, the purple figures on here are published data for these same materials. So that was, considering it's a fairly crude method. And this was 20 or 30 micron diameter craters on these things. So it's useful. We looked at Helge Gitgen. This was something to do with Britta and one or two other people. This is a lake in the far eastern Russian Arctic that's got a series of Tephras in it. We did the leads on those as well. Those are all Kamchatkan lead isotope, published lead isotope data. These are all Alaskan published lead isotope data. And sitting very squarely in one of these is what looks like it might be an Alaskan Tephra. We don't know which one it is in terms of where it comes from, but it's perhaps giving us a clue as to where some of that material comes from based on the lead isotopes. And so on. The errors are not brilliant. They're probably plus or minus 1% or so on the ratios. We're going to hear a talk in a bit about lead isotopes in feldspars, where the precisions are an order of magnitude better done on multi-collector instruments. And I think this might sort of, this paves the way, at least it's a sort of proof of concept for using leads in these things. And you stick them on a multi-collector instrument where you get better precisions, and I'm sure that picture refines really nicely. So a useful, it's a useful tool in the tephrochronologist toolbox. So where are we in terms of what's going on? Well, the later ICP data, it's reproducible. We get good data down to 10 microns in terms of craters, and we can correct fractionation at present, at least based on AthoG. Wide range of trace elements, petrogenesis is great. The TOBA stuff's going to tell us a petrogenetic story at some point, provenance of where these things come from, and we can generate isotope data and so on. But we do need additional matrix-matched natural reference materials, I feel. In terms of what people might do, please try and analyse apheric glass. Use the smaller craters rather than bigger craters because you'll miss the phenocrysts that are in there. If you're using rhyolites, analysing rhyolites, use silicon as an internal standard, and that gets over this phenocryst issue. If you do hit them, they don't have as big an impact and you can spot them more easily. And don't ablate resin, particularly if you want to use calcium as an internal standard. Basalt's a slightly different game. Silicon or calcium are okay, they're both detectable generally, and the resin contribution because of the high calcium in basalts is less significant. But still potentially 1 or 2%. So it could still cause you just a little offset in your data. So to conclude, well, ICP-MS is in good health, it works, it's reproducible and so on. We do need, though, I think, to achieve over the next few years some standardization of what we do. We need appropriate reference material, so bear it in mind if NERC get in touch in the next week or two. I think, though, overall, with a variety of instruments, we're never, ever going to be in that consistent position that the probe community is in, the electron probe community is in, because there's just so much variety of instrumentation out there that will never match that sort of consistent ionization beam and all the rest of it. But again, if we have appropriate reference materials, we'll be able to compensate for the differences between different labs and different instruments and so on. So these things are bloody important as far as I'm concerned, okay? So on that, I'll leave you with a picture of something one or two of us spotted out of the bus yesterday, and this was flying into Seattle a few years ago, Mount Rainier. Thank you for your attention all.